All right, so I have a hand from Sina.
Hi, so my question is towards Professor Erik Curiel. I'm sorry if I didn't pronounce your name right. So you were talking about singularities in your first talk, and you didn't mention anything about the role of entropy, of when the space-time actually goes towards a singularity. How would you presume the entropy to act? Would it decrease or would it increase towards a singularity itself again?
That's thank you. That's a great question. And so I did mention entropy in one place. The theorem by Aaron Wall in the semi-classical context, in fact, depends on the major assumption of the theorem is that the generalized second law holds, and the generalized second law is the statement that a kind of a generalized gravitational entropy, a generalization of the Bekenstein-Hawking entropy for black holes, plus the entropy of ordinary matter, never decreases. But if you're talking about trying to attribute some kind of entropic quantity to a singularity itself, there have several people have thought about doing this, and there has been work that in that direction. But to my mind, none of it is really definitive, I think. But I also don't think that anyone who's working on this would claim it to be. It's very speculative. It's just one of the problems is we don't really know what kind of entropy would be appropriate. Should it be some kind of phenomenological thermodynamical entropy? Should it be some kind of statistical mechanical entropy? Should it be some kind of information theoretic entropy? There are a lot of questions, a lot of very kind of basic fundamental questions one has to try to grapple with before one can even try and build, a mathematical model that would look something like an entropy-like quantity one wants to attribute to an incomplete and extendable curve where curvature may or may not blow up. If you're curious, please email me and I can point you to some of the papers I'm talking about.
Okay, thank you very much. Thanks.
Great. So Erik, I don't see any of their hands raised right now or anything in the chat window. So if you have questions, go for it.
So Mina, you had this great quote from Chandra up about how I can't remember the exact phrase he used, but it was something like one of those shocking or glorious or something like that moments of his professional career was realizing that the Kerr space-time exactly modeled all these astrophysical objects. But of course, Kerr doesn't exactly model stuff, the things we look at, the things that we're pointing the EHT at, because the global structure is wrong. We don't think that cosmological models don't have the right kind of asymptotic structure. We don't have null infinity to define event horizons. So is it the case? So what we're really doing is we're kind of truncating Kerr and just kind of looking at the interior of Kerr and slapping that onto M87, or else we're kind of looking at some kind of approximative or perturbation off of Kerr that destroys the asymptotics that we don't want. And I'm just curious, do you know actually what is, do you know the details, what is actually done there? Like how exactly is Kerr used in constructing these models?
That's a great point. And my impression is that we're just approximating the observer as in the asymptotically flat region outside Kerr. So we're saying that black holes far enough away that we can essentially treat it as in an asymptotically flat geometry. Yeah. But if anyone else knows more about this, please feel free to jump in. That's certainly what was done in my work. Yeah.
Well, as Ramesh once remarked to me when we were talking about something similar, he said, Erik, we are at null infinity compared to M87. So I think that's exactly your point.
Yeah. But that's a great point. Thanks. Yeah.
I think George Ellis has talks sometimes on the effective null infinity, which is something like 3 or 4 light years, according to him. But that's, of course, not a rigorous treatment that, as a philosopher, I'd like to have. But I don't have an alternative to offer.
If no one else has a question right now, I have a few. And my question is, I have a couple for a couple of our speakers. My first is to Lydia. So this is maybe a naive question, but when we talk about using parameters for theory comparison, how broad can we be with theory comparison? I mean, it seems more or less obvious how to parameterize theories that differ from general relativity because of additional terms in the Lagrangian. You just put an additional coupling constant in, and that's now a parameter. But if you think about a somewhat more conceptually different theory, like if you're studying Newtonian mechanics and you somehow want to compare it to quantum mechanics, you're not talking about obviously adding a term into Newton's law. You're talking about a different structure altogether, a completely different theoretical framework. On the other hand, it may be that for certain kinds of systems, you can model, small differences between Newtonian mechanics and quantum mechanics by, in fact, adding a few terms. So I was wondering if you could just talk a little bit more about how we can parameterize, theory comparison for, potential theories of gravity that are just different at a more sort of fundamental structural level.
Yes, that's a great question. So let me step back just a bit and say, I mean, this question is excellent, partly because it gets into the whole reason that I'm interested in this question, which is that partly the use of these parameterized models seems like magic. It seems like you just sort of add in these terms that allow us to test for like deviations from the theory, and it seems to this seems to give us sort of generic hints as to where to go in looking for ways to test the theory or something like that. But I think there's another reason to be interested in it, which is that it can seem a bit like there's an incredibly complex set of questions that's masked by the seeming simplicity of just throwing in a parameter to kind of map this entire set of potential deviations from the theory, right? Because like in philosophy, we can't agree on the question of what theories are equivalent to each other, like formally or empirically, right? So, there's the question of how is it possible, for instance, as you say, to come up with even a model that's consistent with between two theories in two different areas. But there's also a question of if we want to argue that a certain observation is inconsistent with one theory and consistent with another, it kind of depends on how you're going to do the modeling. It depends on how you're going to do the testing, right? There are all sorts of additional questions that come in. And so this is one reason why exactly one reason why I find this so fascinating, is because I think right now, what's happening in this particular area is that people are saying, okay, look, you need to broaden this up and start adding in these sort of error terms and parameters in order to be able to test the theory more broadly. And I think one thing that's going to happen in the kind of, and this was coming also from Sean Carroll's question, one thing that's going to happen in the kind of next generation is that people are going to realize that there's a whole lot of complexity underneath all of that has to be dealt with. And so I have an answer, but it's that answer, which is not really an answer.
Lydia, I actually had a very similar question to what Jacob just asked, and I want to ask it and with a slightly different emphasis.
Okay.
So, what do you think has to be in place epistemically, as it were, for us to have confidence that a kind of a parameterized expansion of a theory like PPE is latching on to the right places, so to speak, in the theory, where to look for like plausible or viable ways that a better theory might differ from the baseline theory, in this case, GR? Or do you think that it's never going to be a case of having confidence that we're latching onto the right places to make the expansions? It's just those are the ones we can handle. You know, we're basically the drunk under the traffic, you know, under the street light looking for the keys because that's where the light is.
Well, yeah. So I want to say that I've observed in this work, I've observed two different ways that people have gone about this, right? So there's two kind of distinct methods that I think may be relevant here, right? And one of them is this: let's throw in a parameter, and this is done in both of the papers that I cited. Let's throw in a parameter in order to then be able to detect deviations if they're there. And this parameter will be we'll be able to make a kind of structural argument that if that parameter is put in the right place structurally, I mean, I'm obviously, this is hand wavy, but if that's put in the right place, then we can make an argument that it's actually going to pick up on something that would be relevantly distinct from the theory, from GR. That way of doing things tends to be the maybe not quite the drunk with looking for the keys, but rather haphazard in the sense that it's like, okay, let's put something in here and see if we get a result. And then the mere fact of a result will be enough evidence to make us look further for some more sophisticated and nuanced, like that'll just be, maybe another metaphor would be, that's where we shine the light to then look for the next type of evidence, but we'll come up with a better way of finding the evidence in that second round. There's another set of arguments that seem to me to be much more sophisticated, which are where, which involve very, very formal arguments where, for instance, and I like Jacob's example of the Lagrangian, right? So where you say, well, okay, look, here's a part of the theory that makes a certain type of dynamical assumption, right? I think Dennis Lamecool has mentioned the assumptions about the fluid dynamics internal to black holes, for instance, and those assumptions, like you could make assumptions that kind of parametrically characterize how that's going to go dynamically, and then hook that up with experimentation in the right sort of way to be able to detect exactly how the parameters are going to vary or vary from or confirm the predictions of GR, right? And that kind of argument, it seems to me, is much more difficult and requires a ton of knowledge of the deep physics of what's going on, right? And so those are kind of really fascinating arguments, because the people who make those arguments have to really get in a deep way how the different elements of the theory work together and what you need to change in order to be able to test for deviations from it, right? And it seems to me that that's a very different kind of reasoning than looking for a confirmation of the theory. It's a way of looking for a broadening of the theory, and in a way that I think is very difficult.
Thanks, Eric and Lydia. So I have a question for Eric, and I think Julia's is still here, so feel free to chime in also, or anyone else who has input into this. But I figure while I have you here, and I've asked you this question sort of very tangentially before, but we have an opportunity now to maybe discuss it, but this question of determinism came up a couple of times in your talk, and certainly singularities can represent a threat to determinism. But I was wondering if maybe you could talk a little more broadly about all the ways that determinism can be undermined in general relativity. And obviously this is a huge discussion, but like paint a ballpark picture, because determinism is obviously a very important idea, and I'm just interested in getting you to lay out like all the different ways that it could fail.
I'm definitely going to need some input from Julius on this one. There are enormous number of ways that something you might want to call determinism can fail in GR. I'll list a few off the top of my head, and then I'll pass the baton over to Julius and see what he has to say. So maybe the most obvious one is that the Einstein matter, the coupled equations, the 3+1 canonical initial value problem isn't always well posed. It can fail. It can be not well posed in the sense of Hadamard for very simple, straightforward kinds of matter systems. Various kinds of perfect fluids don't have a well set initial value formulation. So just from the start, you can have the most brain dead, simple, brutal failure of determinism right there. It can fail in the sense that even if you restrict yourself to well posed Einstein matter equations and well set initial data, then there's a sense in which if you think about GR 4-dimensionally as opposed to 3+1, restricting yourself to globally hyperbolic space-time still doesn't give you determinism. Consider the following example. Fix your favorite globally hyperbolic vacuum space-time. Fix a Cauchy slice. Then, if you the Choquet-Bruhat-Garroch theorem tells you that vacuum solution, if it's maximally extended, is the unique maximal Cauchy development of your Cauchy slice. But now just take some open set to the future of your Cauchy slice and just slap some arbitrary conformal factor onto it. Well, conformal transformations preserve causal structure, so your new spacetime is still globally hyperbolic, but it's manifestly different from your original vacuum spacetime. But it's a perfectly valid solution to the Einstein field equation. I'm never even sure what people mean when they say vacuum solution to the Einstein field equation. Every Lorentzian geometry is a solution to the Einstein field equation. But it clearly isn't the one you get from Cauchy evolving forward your original slice. So then determinism can fail because for various reasons you get Cauchy horizons, most famously in the interior of Kerr and Reiser-Nordstrom. But you can get Cauchy horizons in many other kinds of spacetimes as well. In Taub-Nut, for instance, the t=0 is a Cauchy horizon. So, and the issue of how one extends beyond, or whether one should or can extend beyond a Cauchy horizon is a very subtle one that, again, Julius just I think thought more about than I have, and almost certainly has more to say about than I do. So this is actually a very opportune time for me to hand the baton over to Julius.
Yeah, part of the reason I'm asking is, if one of the objections to taking singularity seriously is that they undermine determinism, I think it's important to ask, like, are there other reasons to worry about determinism beyond singularities as well?
Yeah, I think so. Insofar as I understand, insofar as I'm grokking the spirit of your question, right? I completely agree with you. I mean, determinism is just a non-starter in GR. Whether you care about singularities or not, determinism fails in GR in so many ways that having scruples about it when singularities come up just seems to be hypocritical at best. So I completely agree.
Julius, you want to go next? Yeah, totally. Thanks. Another way in which determinism may kind of fail, but in a nice and deterministic way, is if we do solve something like the initial or characteristic value problem for whatever system we're interested in, and that if that would in a stable way lead to formation of Cauchy horizons, which it may or may not, then that would be something I personally would call deterministic failure of determinism, because sort of given those initial data, we know for sure what's going to happen. A Cauchy horizon will form, and then that's not a very good situation for us. Yet another way in which that may happen is well, that will depend on a particular model, but if event horizons fully evaporate, then arguably we're left with very problematic causal structure. And from a certain perspective, one could argue that both weak and strong cosmic censorship conjectures both fail in that case. And so that's a failure, that's yet another failure of determinism. One more possible way in which determinism could fail was, so like in Erik's discussion, he was talking a lot about spacetime satisfying some maximality condition. And I think a good case could be made that there is no single satisfying condition for what it means for spacetime to be maximal, because all the conditions that we know are either trivially easy to satisfy, or have Minkowski spacetime or a subset of Minkowski spacetime as a counterexample. And moreover, all of those conditions will kind of give us different results in different particular cases. And so on those grounds, kind of committing ourselves to one particular condition and saying that, well, we should consider spacetimes which are as large as possible, that's kind of problematic. But if we do not require something like maximality condition, then we can construct all sorts of monsters using all sorts of techniques. And another another potentially related issue to this is that, of course, determinism is one important thing we care about, prediction is another, but arguably in GR, those two things can come apart in very different ways because we are limited observers with limited access to the past data. And so that, again, can be used to construct all sorts of unpleasantries.
I didn't have in mind limitations on prediction per se in my question, but of course that's also a very important consideration as well. Would either of you say that there's like a really nice definitive treatment of determinism in GR? Like,
I would say look at the two papers by Julius that I cited in my talk. Great. And also for earlier times, the locus classicus is Ehrman, Spang's crunches, whimpers, and shrieks.
Right.
I definitely agree with Ehrman 95 bank crunches, whimpers, and shrieks, but currently I am not aware of like comprehensive good enough treatment because my stuff doesn't count for that.
If you don't mind, Jacob, I want to mention one more way.
Yeah, please.
Which is the way that I mentioned, the very first way that I mentioned about how singularities can arise, and then I quickly dismissed it, saying, but everyone thinks it's cheating, and I actually am deeply dissatisfied with this. So take Minkowski space-time removal point. That's a crazily indeterministic space-time, as indeterministic as you like. But everyone says, that doesn't count. That's unphysical. Why? Are you telling me that there's some kind of a priori principle the universe must satisfy, that it can't have the topology of R4 with some open set removed? I think that people want to say, no, that's cheating. No, you can't do that. No, there's no reason why that can happen, because it doesn't kind of square with how we like to think about mathematics. R4 is natural, whatever exactly that means. R4 with an open set removed isn't. Even the way we describe it, we start with R4, we remove an open set. But they're both just mathematical structures. They're both mathematical objects. It makes as much sense to describe the one as R4 with a set removed as to describe the other as this thing with some points slapped into it. The universe surely doesn't care about our preferred methods of thinking about mathematical structure. So I'm deeply dissatisfied with every argument, and there's usually not even an argument. I'm deeply dissatisfied with every attempt to dismiss these kinds of brute topological surgical constructions that give rise to all kinds of interesting loss of determinism. Thank you for letting me get that off my chest.
It was a pleasure. Sean, and then I have Lydia after Sean.
Thanks, Jacob. Yeah, so I wanted to say something, finally been provoked into saying this thing that I've been thinking all along, which is maybe inflammatory and maybe I think also perfectly obvious. Namely, that to the extent that our interest is in the real world, subtleties of classical general relativity concerning determinism and incompleteness and singularities can only ever be of very limited interest because the world is not classical. Presumably the role of Einstein's equation and classical spacetimes that obey it with appropriate matter sources is as things one discovers as classical limits of some underlying quantum theory of gravity. And given what we think we know about quantum mechanics, that basically leaves us with two choices. There is either real-time evolution with some form of Schrodinger equation with some appropriate Hamiltonian. In that case, there are no singularities. It's just a theorem, right? The Schrodinger equation is linear. You can evolve it in time forever. You never run into any problems. And maybe you get, as approximations to the solutions in some peaked wave packet kind of way, something that looks like you come close to singularities, but you don't ever get there, so whatever. The other possibility is that time is emergent, right? It's not fundamental, h psi equals 0, something like the Wheeler-DeWitt equation, and then, you know, all bets are off. Then you can absolutely have emergent time, and that, oops, I'm joined by a cat. You can't see it, but a cat just jumped on my back. Zoom is editing him out. Yeah, he likes fundamental time better than emergent time. So, but anyway, but that's also a very interesting case, but also very, very different, right? So I think it's interesting mathematically to worry about these issues, but I wouldn't advocate getting too worked up about them until we know more about quantum gravity. That would be my suggestion.
Sean, I want to say I completely agree with like every word you just said. I think it's great, and that's exactly why during the talk when I was talking about the current emphasis in mathematical relativity on differentiability levels, for instance, in addressing cosmic censorship, I find myself baffled. I don't know why these people care so much about proving that something is C0 extendable as opposed to C1, 1 extendable. I don't see what physical difference it can possibly make, given that GR is an effective theory. So
well, likewise, I think it's an answer to questions, not an answer, but the way to answer questions like, should we consider Minkowski space minus a point removed? The answer is, well, what do you get as approximations to the quantum wave function doing things? If you get Minkowski space with a point removed, then that's what you get. You won't, by the way, but if you did, then you would.
I completely agree. There was actually a very interesting paper. It was one of the ones that I had listed in the semi-classical gravity section by Engelhardt and Folkestad that came out very recently, in which they prove a result in ADS CFT like setting that essentially, it's the first result I know of actually that shows that under certain holographic assumptions, trapped surfaces must lie behind event horizons. Now, their proof is actually their theorem is a little bit problematic because there's a sense in which I think it's actually a petitio principii. I think they're actually assuming at least part of what they want to prove. But putting that aside, it's still a really interesting take on the issue, because what they're essentially, the way they interpret the result, and I think they're right to interpret it this way, is they're saying, look, if you have a certain picture of quantum gravity that admits this kind of holographic representation, then what this result is telling you is that it's only non-holographic space-times that can have the kind of a causal pathology that would be represented by having a trapped surface outside of an event horizon. So you would never expect this kind of classical space-time to arise as an approximative limit from the underlying theory of quantum gravity. I think it's a very pretty way of thinking about a lot of this stuff. So yeah, I completely agree.
I see that Carlo has a brief follow-up to this. Carlo, why don't you go ahead?
Yeah, just a finger. I completely agree with Sean, of course. So from the point of view of a physicist, we have strong reason to believe that general relativity fails just for physical reason, not because there are singularities, because we expect quantum mechanical phenomena, and therefore a lot of these arguments are interesting mathematical, but not interesting physically. I still think that even in the way Sean presented the the question originally, there is a replay of the same question in quantum gravity and in what Sean asked, because one of the key points of Erik was just is time evolution something that continuing time evolution past the singularity, past whatever, necessary in some sense? And Erik was saying, well, careful, where are you bringing from the need of this necessity? And when Sean is saying, look, in quantum gravity, again, we have something similar, are we assuming that there is a continuation in time and unitarity in some sense that satisfies this intuition we have about time cannot stop in some funny way? Physics tell us what happened next. Then if you impose that, you're forced to demand unitarity in some sense, a time in which things keep evolving and you don't stop, you don't break predictability. But I'm with you, Erik, in saying, wait a minute, where is this coming from? And Sean is making it clear. I mean, if there are theories of quantum gravity, we don't have an agreed theory of quantum gravity, but there are tentative theories of quantum gravity out there, more than one. And there are some that consider unitarity as needed to make sense a priori of a theory. And there are others in which you don't have unitary evolution. You will do it equation, you have relative evolution rather than evolution in external time. And so how this theory is acceptable or not, which I think is it's a key point. Sorry, it was a finger, I'm going too long. I think you understand what I meant.
Thanks, Carlo. Were there any replies from anybody?
Again, I can only say I completely agree. I'm sorry I can't give more interesting disputes here. But...
Okay. Next, I have Hans, and then I have Lydia after Hans.
Thanks. So I tried to bring in a different perspective or to disagree in some way. I always am nervous that gravity should be a theory of space-time. And that makes me nervous, and for several reasons. I mean, we have spoken about entropy just a little bit, we have touched it only briefly, but entropy for me, the black hole entropy, for example, makes sense only, or is only interesting if it interacts with other forms of entropy, if there's an exchange between different types of entropy, and there's not just this black hole entropy. And if entropy comes into the picture, then of course we expect some kind of second law, and then time is singled out, and I have this 3+1 kind of automatically rather than 4. I mean, otherwise entropy doesn't make much sense for me. So I see a conflict between talking about entropy and having this space-time geometry idea that doesn't really go together for me. It's 3+1, and that has then something to do with Hamiltonian formulations, which are much easier in 3+1, which are only possible in 3+1. But it also has the advantage that one can also formulate dissipative systems there and have other forms of entropy which could play together with black hole entropy. And so I have a certain preference for 3+1, which is unequal to 4, as we have learned, and it obviously is. Yeah? And the other thing is, yeah, these quantization issues. I mean, if I have a fixed Minkowski's background space-time, I feel so much more comfortable, almost in a Kantian sense, or in a special Kantian sense. So it allows me, for instance, to use a different type of geometry. What would I do with a metric? The minimum thing I can do with a metric, if I don't want to interpret it as full Riemannian geometry, is to say it defines a velocity momentum relationship. I mean, it can always be used in that way. It is used in that way. But if I only consider the metric as providing an energy, velocity momentum relationship, which means the relationship between a vector and a covector field. Yeah? So that would be the role of the metric. If I do that, and then I want to do something with that, with Minkowski space, what kind of geometry should I use? And I would use a Young-Mills theory, because that's a beautiful geometry, and that's I mean, we know how to handle that for quantization. And so the obvious the obvious Young-Mills theory is based on the Lorentz group, and it has way too many degrees of freedom. Yeah, that has, what do I know, 24 degrees of freedom or so, way too many for a theory of gravity. So the question is whether one can select an interesting subset of solutions from Young-Mills theory based on the Lorentz group. And I think one can do so in a pretty tricky way, based on something I call composite theories. But that's just the motivation is Young-Mills is something I can quantize. It's of the same type as all the other interactions I described. It's based on a Minkowski space, and I can bring in the metric as for characterizing the Young-Mills fields in terms of the metric. And so that's why I call that composite theory, because you select by expressing the vector variables in terms of basically the metric variables. So I think this is an attractive route to go, and a lot of things seem to be just based on the fact, what was discussed today, seem to be just based on the fact that the metric is a metric in a general relativity sense. Now, if I want a Minkowski background metric and do my theory of gravity there, then the conclusions somehow different concerning the parameter space I would open with that, concerning signals which are maybe not very sensitive. Is that a clear distinction which could be detectable eventually, whether everything lives in Minkowski space with the advantages I have tried to sketch, at least in my opinion, these are advantages. Would that be distinguishable by any of the experiments, I mean, at strong fields and time-dependent fields from a theory like general relativity, or intrinsically done in a metric? That would be my question to the general audience.
You just covered an enormous amount of material there. If you don't mind, I'm going to go back to I'm going to jump back to the very start of your question, and you mentioned something about you talked about entropy, and I'm curious. You said that for you, it's fundamental for entropy that you have a notion of time evolution. And I think I'm actually quite old-fashioned in this way, and I mean really old-fashioned, like 19th century old-fashioned. That for me, entropy is the principle of entropy non-decrease is not the most interesting thing about entropy. It's in the 19th century, people didn't call the principle of entropy non-decrease the second law. They called the Kelvin postulate what we now call the Kelvin postulate and the Clausius postulate the second law. The Kelvin postulate says that there is no transformation that will extract heat from a source that is at a constant temperature throughout, transform it entirely into work, and leave the rest of the world unchanged. And the Clausius postulate says that there's no transformation that will whose only sole result is that heat flows from a colder body to a hotter body. So to me,
and comment directly on that. May I say something about that? Just a direct comment on what is the most important thing about entropy. The most important thing about entropy for a non-equilibrium thermodynamicist like me is that it generates irreversible dynamics. Energy generates reversible dynamics, and entropy generates irreversible dynamics. And that's the most
entropy places constraints on what allowable transformations are among states of a system. And I don't see why that is not perfectly applicable to systems that include black holes. You seem to suggest that the entropy of that the Bekenstein-Hawking entropy somehow you couldn't accommodate that in this idea that entropy is essentially constraint, that the fundamental fact about entropy is that it constrains what allowable transformations are. But why do you think that Bekenstein-Hawking entropy can't play that role?
No, it can be there. I only thought it's more interesting if there are other forms of entropy, so that I don't only have the overall production of entropy, but I can have exchange, conversion between different types of entropy. I mean, think of energy. I mean, energy is interesting, not if I just look at kinetic energy or something like that, but it's conversion between different forms of energy which makes life more interesting. And the same is true for entropy. Yes, I think it's a bit boring if I only have the black hole entropy, but we know it plays somehow together with thermal entropy. and so on. So life is much more interesting if on top of the overall entropy production, I have conversion between different forms of entropy. That's all I mean.
I completely agree, but why doesn't that happen when I just take your favorite highly entropic material system and toss it into a black hole? Why isn't that conversion of, say, you know, whatever your favorite entropy is, thermodynamic, Boltzmann?
That's why I expect it to happen, why I expect it to be important, and that's why I think 3 + 1 is important, and it's not really 4, because if that's the consequence of trying to find distributive equations which describe the situation, that I think forces me into 3 + 1 rather than 4. That's one of the consequences.
I want to throw this open. I want to hear what other people have to say about this, if other people want to jump in.
Well, if people have thoughts, we can return to this discussion. I did have a hand from Lydia. So Lydia, why don't you ask your next question? And if people want to return to this, please raise your hand or put a chat message in the chat box. Lydia?
Yeah, so I do want my life to be interesting, but I don't have a specific comment. Thank you. So my question is for Mina Himwich. Am I pronouncing your name properly? Sorry.
Yep, that's right.
Okay, so yeah, so my question was about, I mean, I love the sort of real-time demonstration of via Pharrell of how the different strains of the Fourier analysis get put together into a single image. But I wondered, this is honestly just curiosity on my part, since I can talk to someone who knows about this. From what I understand of the EHT methods, right, they separate out the low and the high band frequencies, right? And then there's a correlator, like a massive, this is another one of the places where you have to use a supercomputer, and there's like a massive correlation between the two, and so it's not quite that just things are sort of superimposed upon each other, but rather there's kind of a whole method of like combining the measurements. And I just wanted to invite you to say more about, like, is there anything in particular for your project that seems sort of particularly relevant, arising from those methods of correlation of the signal, or just, I wanted to invite you to say something more about that because it's fascinating to me.
Yeah, so you're right. The signals can be correlated between, the different telescopes, so that all the data is taken at the separate sites. Sorry, there's some background noise here, so I'm trying to keep muted as much as possible. But yeah, the data is correlated between the different sites. And one actually really important effect is there's atmospheric scattering that occurs. And so when you're measuring a Fourier transform, it has both a phase and a magnitude. And the atmospheric scattering is totally, like, affects the phase. So you can't really get phase information reliably. And one, like, of your Fourier transform. So usually a lot of the reconstruction is done using the amplitude of the Fourier transform. And also there are ways of canceling out the contribution from phase using something called a closure phase, where you compare the difference in the phases between a triangle of sites. And observables, the most robust observables are the ones that don't involve phase information in the Fourier transform. And it turns out that this polarization observable actually does not involve any phase information. So yes, so the project I worked on identifying the spin in the Fourier transform doesn't rely on any absolute phase information. And yeah, so that's another big question in VLBI, and there are people who spend their entire career just subtracting out atmospheric noise. So Yeah.
That's just a quick, that's fascinating that because that's counterintuitive that the measurements wouldn't involve any of the phase information.
I had a technical question for Mina. On one of your slides, I think it was the slide on you were talking. I think it was the large N slide. We were talking about how at large N, we expect that. I think the statement was that we expect that the large N photons have the same momenta. And then there was a statement that we also expect the intensities to be the same at large N. And I guess I was just wondering if that was obvious or if that's not, I mean, it's not obvious to me, but if there's an obvious explanation for why we expect the intensity to be the same. If you just maybe explain a little bit about that, because it's very curious, the idea that all these rings at large N have the same intensity. I was wondering if maybe you could explicate the physics behind that a little.
Yeah, I guess, I mean, the way that I think about it is sort of you can imagine shooting a light ray back into the geometry around the black hole. And if the initial, the trajectory is determined by by like where it arrives, its momentum, and that tells you to conserve quantities of the geodesic. And so if they're all traveling the same way through the geometry, they're picking up they're passing through the matter in the same way. So you imagine like, it's this thing called ray tracing, where you imagine like loading photons onto the rays in the geometry. And so if things are passing through the same way, all the light will get loaded on the same way. And that's why the intensity is the same. Yeah, does that make sense?
Yeah, that clarifies it, thanks.
Yeah.
Can I had the same question, but I haven't understood the answer. Are you assuming that they start? That there is an assumption about Jacob is faster than me. He has got the answer, I haven't.
Yeah, so I'm thinking there are two ways of thinking about it. You can think about you're at the observer and you're tracing things back into the geometry around the black hole. Or you can think about you start at some specific point and then you go around, like there's light that's emitted at a certain point and goes to the observer. And so a certain point can emit light that executes any number of orbits.
Okay, got it. Okay.
And, yeah, and a trajectory that starts from me can pick up light that underwent different numbers of orbits too.
I got it. Thank you.
Great. All right, are there other questions? Oh, Logan, go ahead.
Thanks. So I think these are questions for Erik. So one is the scenario of the time reverse of the collapsing star, right? So this is the, and it explodes out with, I don't know, Nixon or whatever, right? I wondered about comparing that with the time reverse of the classical Newtonian system of the, the hemisphere and the frictionless block that slides up and comes perfectly to rest at the top of the sphere, right? And then the time reverse of that is it sits there and then all of a sudden it goes off in some direction.
This is the Norton's dome, right?
Right. Yeah. And then my second question is, you raised this question about the Navier-Stokes, the sort of analogy or disanalogy with the Navier-Stokes. And I wonder, so if you started the Navier-Stokes evolution with sufficiently small initial data, we know it will be well behaved, right, under some, limiting conditions. I believe, I would imagine that something like that is the case. And I wonder, is there an analogy there with, of course, in GR, if you're sufficiently close to the Minkowski space or certain other kind of well-behaved, we believe certain other well-behaved asymptotically flat, kinds of solutions that you don't actually develop singularities. So like, I'm wrestling with this notion of like a singularity is when something bad happens. And we know that that if you start with something sufficiently close to Minkowski, nothing bad happens, right? That in fact, you do get geodesically complete spacetimes. And so those are the two kind of questions about sort of analogies or disanalogies between those other systems.
So the question about Navier-Stokes, well, in full generality, of course, it's not known. That's in fact exactly the Clay Institute's Millennial Prize. if you know the answer, you've already won $1 million because that I believe is what the Clay Institute is offering for solving that problem. But and so in fact, people and the question that the Clay Institute actually has posed is of course quite carefully formulated, because it's well known that there are very specific, very finely tuned initial data for Navier-Stokes that will, in a finite amount of time, give you divergent behavior in any of the quantities that Navier-Stokes attributes to its systems. So you have to be careful and say, well, we know that there are very finely tuned initial data that behave badly, but do generic initial data, if you slightly perturb this badly behaved initial data, will you get good behavior? And so that in full generality is not known. But the question about Minkowski spacetime and whether or not if you start with the spacetime close enough to Minkowski spacetime, will you get good behavior? Well, the issue there, for me at least, is I don't really know what it means for another spacetime to be close to Minkowski spacetime. There's the very beautiful and famous work by Kleinerman and Christodoulou, who proved what they call the nonlinear stability of Minkowski spacetime. That when they impose that they consider a certain family of spacetimes that they want to say are close to Minkowski spacetime, based on norms on the family of spacetimes that they construct using Sobolev measures, which it's a very complicated, and this is actually the very complicated, messy part of their otherwise very, very beautiful idea. But that's actually where the problem is for me, because these Sobolev norms that they put on the family of spacetimes that they want to use to say, look, Minkowski spacetime is stable under small perturbations. In fact, under fully nonlinear perturbations. I have no idea what those norms mean physically. If you, for instance, if you're talking about Navier-Stokes and you say, I'm gonna define a norm on the solutions for the Navier-Stokes equation for this kind of let's fix a spatial geometry for how the fluid flows around. Let's fix some parameters for the fluid, like its shear viscosity, its bulk viscosity, and I'm going to put a norm on the solutions for Navier-Stokes for that geometry for those viscosity parameter values, and the norm is the soup norm. I know what that means physically. I can tell you what that means physically. What it means for two solutions there to be close to each other. I have no idea what these Sobolev norms mean physically. I have no idea what it means for two spacetimes to be close in the Sobolev norm. It's utterly opaque to me. So the issue for me is whenever these extraordinarily deep mathematicians prove these amazing results about this kind of stability, I have no idea what it means physically. So insofar as there's kind of intuitive idea of what it means for there to be a small perturbation of Minkowski spacetime, we all want to say, yeah, well, that can't develop singularities, right? But as soon as you try and make it precise enough to prove a real rigorous mathematical result about at least all the attempts that I know of, I get lost. So
can I just quickly? It sounds like you're sort of denying anything that involves sort of comparing one spacetime with another spacetime. I mean, that's the.
No, I'm not.
I mean, they're doing that. They have to do that because they have to set some kind of coordinate, right?
Yeah, I'm not saying that in principle it can't be done or it's never done, because in fact it is done. Cosmologists do it all the time, I think, in very principled, powerful ways. When they construct a perturbation, inhomogeneous perturbations off of FL or W to give up in some sense a more realistic model of the actual world, which isn't perfectly homogeneous. So there is a sense in which, in very specific cases, for very specific purposes, there are well-defined, to me, physically perspicuous notions of what it means for two spacetimes to be close to each other in the relevant sense. But in the kind of generality you're asking about, I think, when you say I want to know whether small perturbations off Minkowski spacetime always lead to non-singular behavior, I don't know how to answer that in any generality.
All right, so I don't see any hands currently up, but I do remember Susan raising your hand, I think after maybe Erik's talk. Am I misremembering this, Susan?
No, Eric, I put the question in the chat to you. I don't know whether you think it's worth answering or not.
No, I thought it was an interesting question. So,
If you want to raise it now, we'd all like to hear it.
Okay.
We have about 4 minutes left.
Yeah. Okay. Do you have it in the chat, Eric, or shall I find it again? Okay. What I asked was, do you think that the people working on this question know about the analogous singularities in fluid dynamics and the physical phenomena that correspond to them? And if so, why doesn't that matter? Is it considered relevant or is it dismissed? And I sort of thought that this would, in a way, support your view.
So yeah, my sense is, I mean, I don't want to speak for these people, but I have spoken with them, and so one, just they're all good physicists. I can guarantee you that they know quite a bit about Navier. Well, not every physicist knows everything about every physical theory, but they know that Navier-Stokes solutions blow up. They know there are these singularities in other kinds of theories. They know that these kinds of divergences appear, you know, in non-space-time theories. My sense is that they tend to assimilate. A lot of relativists, you think about this, do tend to assimilate in their mind the kind of blow up that happens, say, in kinetic energy terms in a Navier-Stokes solution to curvature blow up in Schwarzschild, say. And I think that it's a misleading picture to have for the reason that I said. In a theory like Navier-Stokes, when a term blows up, I can point to the place in space and the moment in time when it actually hits infinity, at least, you know, in the model. Obviously not in the real world, we think. But that's exactly what you can't do in general relativity. Nothing ever goes to infinity at any point in a relativistic space-time. At least no measure of curvature does. There actually in the remaining 1 minute, I can't help. I want to mention there's this really interesting class of singularities that was characterized in 2004, 2005 by John Barrow that he called sudden singularities, which occur in cosmological settings and are quite different from the kinds of singularities I was talking about in the talk today, but are clearly very closely related. They arise when essentially derivatives of the Hubble parameter diverge. But derivatives of the Hubble parameter are proportional to some really physically important quantities like spatial pressure. So it can happen in these cosmological models that spatial pressure can diverge. It can actually go to infinity, you know, right in the middle of space-time. But the space-time is geodesically complete. There are geodesics that just pass right through that point where the spatial pressure diverged. So you can get this really weird, seemingly pathological behavior in GR spacetimes, but they're not associated with incomplete and extendable curves. So it's really hard to know what to say about that.